Imagine that a message leaves Earth tonight. Not a weak message, not a desperate whisper, not a radio leak dissolving into noise, but a deliberate signal. Bright, focused, engineered by a civilization that has learned to speak across interstellar space. It carries instructions, maps, a history of our species, perhaps even a simple command from a government that believes it has become more than planetary. The beam climbs above the atmosphere, leaves the moon behind, passes the orbit of Mars, crosses the outer planets, enters the dark beyond Neptune, and then begins the real journey. For 4 years, it travels before it can even reach the nearest neighboring star. For 26,000 years, it must travel before it reaches the region of the galactic center. For 100,000 years, it must travel before it could cross the visible disk of the Milky Way from one side to the other. And during all that time, nothing has gone wrong with the signal. It has not stopped. It has not slowed. It has moved at the fastest speed the universe permits. That is the first uncomfortable fact. Even light is slow when the stage is a galaxy. Science fiction usually begins after that fact has been softened. It gives civilizations shortcuts, hyperspace lanes, wormholes, warp drives, jump gates, folded space, ancient relays, engines that treat light years like oceans and centuries like inconvenient weather. Those stories are not foolish. They are expressions of a human need to imagine connection. But if we remove the shortcuts and ask what known physics actually allows, the galaxy becomes something very different from an empire waiting to be claimed. It becomes an isolation machine. The debatable claim is not that interstellar travel is impossible. That would be too blunt and probably wrong. Robotic probes may one day cross to nearby stars. Small laser-driven sails may someday leave the solar system at a meaningful fraction of light speed. Very advanced civilizations could plausibly build settlements around other stars, especially in dense local neighborhoods where distances are only a few light-years. The strongest objection to a pessimistic view is real. Expansion does not need to be fast, centralized, or human-like. It could be slow, automated, distributed, patient, and almost biological, with each colony or machine colony sending descendants outward in a wave that eventually touches much of the Milky Way. That objection matters. It prevents the easy answer. The galaxy may not forbid motion. It may not forbid settlement. It may not even forbid the slow diffusion of life or machines across enormous distances. What it appears to resist, under the physics we can actually test, is something more specific: a coherent galactic civilization, a functioning empire, federation, or unified culture able to control, trade, govern, synchronize, or even remain mutually intelligible across the entire Milky Way. The public story often asks, can we reach the stars? The sharper question is colder. If some intelligence reached many stars, would those stars still belong to one civilization? Or would the act of reaching them destroy the unity it was meant to create? To answer that, we have to begin with the arena itself. The Milky Way is not a neat spiral painted on a poster. It is not a decorative disk with stars placed conveniently at regular intervals. It is a rotating, dusty, uneven, three-dimensional structure, more than 100,000 light-years across, filled with perhaps 100 to 400 billion stars, clouds of gas, dark lanes of dust, compact clusters, dead stellar remnants, brown dwarfs, rogue planets, magnetic fields, radiation environments, and a dark matter halo extending far beyond the visible light. It is familiar because we live inside it. It is not friendly because of that familiarity. Our solar system sits in a minor structure called the Orion Spur, between larger spiral arms. From here, the galaxy looks like a pale river of starlight because we are looking through the disk from within. But that river is not a road. It is a projection of billions of separate suns at different distances, moving on different orbits, hidden and revealed by dust, all circling the galactic center over hundreds of millions of years. The Sun itself takes roughly 250 million years to complete one orbit around the Milky Way. During the time it takes the Sun to go around once, entire biological lineages can rise and vanish on Earth. A galaxy is not a country. It does not sit still while you build across it. Near the Sun, the nearest star system is Alpha Centauri, and its small red dwarf member Proxima Centauri lies about 4.25 light-years away. That sounds almost close until the phrase light-year is restored to its actual meaning. 1 light-year is about 9.46 trillion kilometers. The nearest star is therefore not a neighboring island. It is a target separated by more than 40 trillion kilometers of mostly empty space. The most distant human-made spacecraft are not even 1 light day from Earth yet. Voyager 1, launched in 1977, has traveled for nearly half a century and has only begun its passage through interstellar space. Parker Solar Probe, falling through the Sun's gravity well, has become the fastest human-made object, racing through the solar atmosphere at hundreds of thousands of miles per hour. And still, in the units that matter for interstellar civilization, these achievements are tiny. They are magnificent first steps inside one star system, not proof that a galaxy can be crossed, settled, and governed. The gap between crossing a planet's neighborhood and crossing the stars is not a gap of ambition. It is a gap of scale. This is where one of the most common mistakes enters. People use the word colonization as if it were one thing. It is not. There are at least 4 different ideas hiding inside that word, and each one is harder than the last. The first is detection. A civilization notices another star, studies it, maps its planets, measures its spectra, perhaps detects oxygen, methane, water vapor, city lights, industrial gases, or some artificial night-side glow. Detection requires instruments and patience. It does not require crossing the distance. The second is exploration. A probe is sent. It may fly past the destination at high speed, gather data for a few hours, and spend years transmitting a tiny fraction of that data back home. Exploration is hard, but it is the least impossible form of interstellar action. The payload can be small. It does not need to stop. It does not need to survive forever. It only needs to arrive functional enough to look. The third is settlement. Something must stop, build, and continue. That is a completely different problem. A settlement mission must carry or recreate agriculture, power generation, repair systems, manufacturing, medicine, governance, education, reproduction, and the knowledge needed to recover when something breaks. It must survive not as a heroic expedition, but as a new branch of civilization. The fourth is empire. Empire is not merely many settlements. Empire is a network that still behaves as one thing. It requires communication, coordination, shared standards, some recognizable political or cultural continuity, and the ability for one region to influence another before the situation has become ancient history. Empire is not a bigger settlement. It is a different physical class of problem. Confusing these four categories makes the future look easier than it is. A civilization might detect thousands of worlds. It might explore dozens. It might settle a few. None of that automatically gives it a galaxy. The first wall is the speed of light. In everyday life, light seems instantaneous. A room turns bright when a switch is flipped. A signal crosses a city in a fraction of a blink. Even radio communication with satellites feels fast enough to be almost immediate. But the universe has no obligation to preserve human intuition when the distances become astronomical. Light takes more than 8 minutes to reach Earth from the Sun. It takes hours to cross the outer solar system. It takes years to reach the nearest stars. It takes tens of thousands of years to cross meaningful galactic distances. Nothing with mass can be accelerated to the speed of light. The closer an object gets, the more energy is required for each additional increment of speed. This is not a practical failure of our current rockets. It is built into special relativity. A massive ship does not merely need a better engine to reach light speed. It would require infinite energy. The word infinite is not dramatic decoration here. It is what the equations say. So any ship must travel slower. At 1/10 of light speed, the nearest star can be reached in a few decades. That is extraordinary, if it can be achieved. But the full width of the galactic disk would still require about 1 million years. At 1% of light speed, a galaxy crossing becomes 10 million years. At 1,000th of light speed, it becomes 100 million years. Those numbers are not inconvenient. They are civilizational acid. They dissolve almost everything we normally mean by mission, plan, command, return, and continuity. A 1 million year voyage is longer than the existence of Homo sapiens as a technological species by an absurd margin. A 10 million year voyage reaches back beyond the human lineage as we know it. A 100 million year voyage is geological. It belongs to continents and climates, not institutions. One might answer that no one needs to cross the whole galaxy at once. Expansion could be stepwise, star to star, like a slow fire moving through dry grass. That answer is serious. It is the backbone of many optimistic Fermi paradox arguments. If each settled system sends out a few more settlements, then the expansion front may move much faster than any single ship crossing the galaxy end to end. It does not require one civilization to build a ship for every star. It only requires replication. But notice what this changes. It helps diffusion. It does not rescue coherence. If a daughter colony sends its own daughter colony after centuries of local development, and that colony sends another after more centuries, the frontier may move outward. But with every generation, the chain becomes less like a command structure and more like biological ancestry. The descendants may share an origin. They do not necessarily share laws, language, values, technology, or even body plans. If the wave continues long enough, it may populate space while destroying the very unity that empire requires. The galaxy can be seeded without being ruled. Energy is the second wall. A spacecraft is not a thought. It has mass. It must be accelerated. If it is meant to stop, it must be decelerated. If it carries people, habitats, shielding, industrial equipment, or anything more substantial than a wafer-thin probe, the energy cost becomes enormous almost immediately. Take a deliberately modest example. A vessel with a mass of 1,000 metric tons. That is not a world ship. It is not a city. It is only about the scale of large human-built structures and far smaller than any credible self-sustaining colony vessel would likely need to be. Accelerating that mass to 10% of light speed requires on the order of 10 to the 20th joules of kinetic energy before inefficiencies, fuel mass, deceleration, shielding, and waste heat are included. That is comparable to a large fraction of the current annual energy consumption of human civilization. One ship, one acceleration, not a fleet, not a return trip, not a colony. And the calculation gets worse when the ship carries its own fuel. The rocket equation is merciless because fuel has mass, and fuel used for braking must be accelerated during launch. If you add more fuel, the ship becomes heavier, requiring still more fuel. Chemical rockets collapse immediately under this burden. Nuclear fission improves the numbers, but not enough for fast interstellar colonization. Fusion is far better, and may be the first propulsion concept that makes serious interstellar travel physically discussable for large payloads. But fusion still demands massive fuel reserves, extreme engine performance, and efficiencies well beyond anything humanity has demonstrated. Antimatter looks tempting because matter-antimatter annihilation converts rest mass into energy with unmatched completeness. But antimatter is not a fuel lying in convenient lakes around the galaxy. It must be made, stored, and handled. At present, making even tiny amounts is fantastically inefficient. Future technology might improve production by many orders of magnitude, but antimatter does not remove the need to supply energy. It simply shifts the burden into fuel manufacturing, containment, safety, and industrial scale. Laser sails offer a more elegant escape from one part of the rocket equation. A tiny probe can carry no fuel at all, pushed by a powerful beam from its home system. Concepts like gram-scale light sails accelerated to a fraction of light speed are fascinating because they show that interstellar exploration may not be pure fantasy. But the word gram is doing much of the work. A nanocraft is not a colony. Scaling a beam-riding sail from grams to thousands or millions of tons does not merely require a bigger laser. It requires power, optics, heat management, beam stability, and pointing accuracy on a scale that approaches stellar engineering. What looks elegant for a tiny flyby probe becomes monstrous for settlement. The strongest pro-expansion view responds with megastructures. Build Dyson swarms, capture the energy output of stars, manufacture fleets from asteroids, let robotic industry multiply until the energy and material limits are no longer human scale. That counterargument is not foolish. A civilization thousands or millions of years older than ours may treat planetary-scale industry as primitive. The sun releases more energy every second than humanity uses in many thousands of years. A civilization able to harvest even a small fraction of a star would have capabilities we can barely imagine. But even stellar energy is local. A Dyson swarm around one star helps within that star system. It does not cheaply accelerate an empire across the galaxy. Energy cannot be shipped across light years without loss or without requiring carriers that themselves consume energy to travel. Beams spread. Fuel shipments cost fuel. Batteries have mass. The galaxy is not wired like a continent. Each star system is closer to an island with its own sunlight, its own material inventory, its own constraints, and its own thermodynamic accounting. A rich system can fund its local ambitions, It cannot easily become the power plant of distant settlements, separated by hundreds or thousands of light years. This creates a bootstrapping problem. To build galaxy-scale infrastructure, a civilization needs galaxy-scale reach. To gain galaxy-scale reach, it needs infrastructure that is already distributed across many stars. The first steps may be possible. The scaling is where the dream breaks. The third wall is the medium itself. Interstellar space is often described as empty, but empty does not mean harmless. A spacecraft moving at high fractions of light speed sees even sparse gas and dust as a high-energy particle beam. Hydrogen atoms in the interstellar medium strike the forward shield like radiation. Microscopic dust grains carry devastating kinetic energy at relativistic speeds. A grain that would be harmless at walking speed becomes a bullet. A larger one becomes an explosive event. For a tiny probe, clever shielding and trajectory choices might make the risk acceptable. For a large vessel with a broad cross-section, traveling for decades or centuries, the accumulated hazard becomes severe. The faster the craft moves, the worse the impacts become. The slower it moves, the longer it remains exposed. Again, the universe refuses to offer a free direction. Speed reduces transit time while increasing impact energy and propulsion cost. Slowness reduces impact severity while increasing exposure time and system degradation. Then there is ordinary failure. Every machine decays. Electronics suffer radiation damage, materials fatigue, seals lose integrity, bearings wear, coatings erode, software accumulates faults, cryogenic systems fail, stored biological material degrades, shielding takes impacts. A spacecraft that must function for 50 years is already an engineering challenge. A spacecraft that must function for 500 years becomes a civilization in miniature, carrying not just spare parts, but the capacity to diagnose, manufacture, and replace critical systems. A spacecraft that must function for 5,000 or 50,000 years becomes less like a vehicle and more like an artificial ecosystem locked in a war against entropy. That war can be fought locally with energy and maintenance. But interstellar ships in transit cannot rely on supply chains. There is no port halfway to a star unless you built it, and building it requires another mission. Maintenance systems must maintain the maintenance systems. Factories must repair the factories that produce the replacement parts. Knowledge must be preserved across generations of crew or across autonomous machine operation. At sufficient duration, reliability is no longer one engineering discipline. It becomes the central mission. The fourth wall is communication. This is the wall that most deeply damages the idea of empire. Travel can be slow and still arrive. Communication, if it is too slow, loses meaning. A message to Proxima Centauri takes more than 4 years, one way. A reply takes another 4. That is already longer than many human political administrations. At 50 light years, a question takes half a century to arrive, and any answer returns after a century. At 500 light years, the round trip is a millennium. At 10,000 light years, it is 20,000 years. At the full span of the galactic disk, a round trip is 200,000 years. What does governance mean when every instruction arrives as archaeology? A central authority receiving a report from a colony 1,000 light-years away is learning about events that happened 1,000 years earlier. By the time it sends a response, and the response arrives, 2,000 years have passed at the colony. The crisis that motivated the report has ended. mutated, been forgotten, or become foundational mythology. The people who sent it are dead. Their institutions are gone or transformed. The language may have shifted. The social problem that required advice may no longer exist. This is not a bandwidth issue. A laser link could send enormous amounts of data. It would still be old data. The issue is latency. Information arrives too late to guide action. On Earth, coordination depends on the current state of other nodes. A supply chain works because factories, ports, warehouses, and buyers update one another quickly enough for decisions to matter. A military command structure works because the commander has some usable picture of where forces are now. A financial system works because price information is fresh enough to influence exchange. When the information delay exceeds the timescale on which the system changes, coordination collapses. At galactic distances, the delay does not merely exceed the rate of change, it humiliates it. A civilization may slow itself down. Post-biological minds could choose long decision cycles. Artificial intelligences might sleep between messages. Societies could become extremely conservative, building institutions designed to last for millennia. This is the strongest counterargument to the communication problem. Perhaps a civilization not shaped by human biology would not care about 100-year replies. Perhaps it would treat a millennium as a committee meeting. But even that only stretches the coherent radius. It does not remove the horizon. A civilization whose institutions can tolerate 50-year round-trip communication might coordinate across a few dozen light-years. One that tolerates 500-year delays might maintain a loose region a few hundred light-years wide. One that tolerates 5,000-year delays, a wildly generous assumption, might coordinate across a few thousand light-years. The Milky Way is more than 100,000 light-years across. Even immortal patience does not make the galaxy small. The mathematics of networks makes it worse. 10 settlements have 45 pairwise communication links. 100 settlements have nearly 5,000. 1,000 have nearly 500,000. 10,000 have almost 50 million. Every link has its own delay, its own history, its own cultural context, its own translation burden. A central archive trying to maintain an accurate picture of the whole network does not possess a map of the present. It possesses a layered fossil record. Recent data from nearby systems, centuries-old data from middle-distance systems, and ancient data from the far edge. The result is not an empire, it is a museum with antennas. This is why interstellar trade, in the familiar physical sense, also fades under scrutiny. Trade works when the value of a delivered good exceeds the cost of moving it. Across oceans, that can be true. Across space between planets, it might be true for extremely rare materials or specialized equipment in a mature solar system economy. Across light years, it becomes difficult to justify for almost any ordinary physical good. Sending 1 kilogram of cargo to another star at useful speeds requires far more energy than the cargo is likely to be worth when it arrives. Gold is not worth shipping between stars if the destination system has asteroids. Water is not worth shipping if comets exist locally. Iron, carbon, silicon, aluminum, oxygen, hydrogen. The basic materials of civilization are widespread. The rational strategy for an interstellar colony is not import dependence, it is local extraction. Every serious settlement must become materially self-sufficient as quickly as possible, because waiting decades or centuries for shipments is a fragile and expensive way to die. Once settlements become self-sufficient, the economic glue of empire weakens. They do not need each other in the way cities on Earth need global trade. They may exchange information, art, history, and occasional rare designs, but those exchanges arrive late and must be adapted to local conditions. A machine design optimized for one star system may be useless in another with different available materials, gravity, radiation, atmospheric chemistry, or industrial standards. Knowledge can travel at light speed. Context does not. Standards drift. On Earth, maintaining shared standards is active labor. Units, data formats, manufacturing tolerances, docking systems, software protocols, legal definitions, scientific notation, and medical classifications require constant revision and agreement. That work is possible because communication is fast. Across interstellar distances, every update arrives late. A standard published by a central body might take 200 years to reach a distant colony. By the time it arrives, the colony has solved its own problem differently and built infrastructure around that solution. Adopting the central standard would mean tearing out a mature local system to obey a document from the past. It will not do that unless the benefit is overwhelming. Usually, it will not be. So docking ports diverge, data systems diverge, languages diverge. Units of measure may remain mathematically convertible, but the conceptual world around them shifts. Biological populations adapt to local environments. Machine intelligences rewrite themselves to suit local hardware. Educational traditions change. Mythology changes. The meaning of home changes. At some point, the common origin remains true, but becomes irrelevant. This is what fragmentation looks like. Not collapse, not disaster, divergence. A colony around a red dwarf develops technologies for flare protection, tidally locked habitats, and low-light energy capture. A colony around an F-type star develops radiation management and fast adaptation to a shorter stellar lifetime. A colony in a dense multi-star region builds navigation and shielding systems for a busier gravitational environment. A colony around a quiet K-dwarf builds long-term stability into every institution. After 5,000 years, they are not branches of one civilization. They are different answers to the same cosmic problem. The word empire assumes the opposite. It assumes that differences can be contained by law, force, money, identity, or communication. But across the galaxy, every one of those tools weakens with distance. Force is not useful if fleets take centuries to arrive. Law is not useful if the court's decision arrives after the society has changed beyond recognition. Money is not useful without a shared financial system and timely trust. Identity is not useful if the descendants no longer recognize the story of origin as politically binding. Communication is not useful for command if it arrives too late to command anything. Now the optimistic case returns in its strongest form, self-replicating probes. A robotic probe that can arrive at a star system, mine local asteroids, build copies of itself, and send those copies outward could, in simple mathematical models, spread through the galaxy without needing large biological crews, centralized supply, or constant communication. It would be a technological spore. It would not need empire because it would be a process. This is one reason the Fermi paradox has bite. If such probes are possible and cheap enough, why do we not see them? Why is the solar system not full of ancient machines? This is a powerful objection because it correctly shifts the discussion away from human-shaped ships and toward automation. It admits the scale and answers with replication. A single seed becomes many. Many become more. The galaxy can be touched without a central plan. But again, touching is not ruling. Self-replicating probes face their own limits: resource variability, manufacturing errors, evolutionary drift in code, radiation damage, local hazards, competing instructions, containment risk, and the problem of making a system robust enough to copy itself across millions of years without mutating into something useless or dangerous. Even if such probes work, the result is not a coherent civilization unless they maintain shared goals and reliable communication across the spreading wave. If they are fully autonomous, they become a machine ecology. If they require oversight, light speed delay breaks oversight. If they adapt locally, they diverge. If they do not adapt locally, many fail. The best case for galaxy-wide presence is therefore not a single empire. It is diffusion by descendants that eventually cease to be the same thing. That distinction matters for the Fermi paradox. The common question asks why, if the galaxy is old, no civilization has spread everywhere. One possible answer is that the premise is wrong. Civilizations may spread locally. Probes may travel. Settlements may form. But the galaxy may naturally divide them into islands. From any one island, the rest of the galaxy remains mostly silent, not because nobody exists, but because distance, delay, divergence, and detectability conspire to hide them. Signals also fade. A civilization is not automatically visible just because it is technological. Human radio leakage, often imagined as an expanding announcement of our presence, becomes faint quickly. Deliberate beacons can be powerful, but why maintain them for millions of years? A beacon requires energy and purpose. If it is aimed narrowly, most listeners miss it. If it broadcasts broadly, energy spreads thinly. If it uses communication methods optimized for efficiency, it may look less like a lighthouse and more like compressed noise. If advanced civilizations move toward tight laser links between nearby systems, their communications may be nearly invisible unless the beam crosses us by chance. A galaxy filled with local civilizations could still look quiet from Earth. The silence would not prove loneliness. It would prove that cosmic listening is hard. Entropy is the final wall, and it is the least cinematic because it works slowly. A starship can be dramatic. A signal delay can be tragic. Entropy is patient. Every ordered structure has a maintenance cost. A habitat must hold pressure. A farm must recycle nutrients. A reactor must remove heat. A data archive must correct errors. A society must train replacements. A colony must keep its machines from degrading faster than it can repair them. None of this is optional. The second law of thermodynamics is not a poetic idea about decay. It is the statistical reality that ordered systems persist only by using energy to export disorder elsewhere. On a planet like Earth, a biosphere performs vast maintenance automatically. Oceans buffer temperature. Microbes recycle nutrients. Weather redistributes heat. Rock cycles regulate carbon over geological time. A space colony or alien settlement lacks most of that inherited infrastructure unless it builds and maintains it artificially. That makes survival possible, but expensive. A self-sustaining colony must be able to repair its reactors, fabricate chips or whatever replaces chips, maintain pressure vessels, produce food, handle waste, prevent ecosystem collapse, educate new generations, preserve technical knowledge, adapt to new hazards, and do all of this without assuming rescue. If its technology is too complex for its population and resource base to reproduce, it carries a hidden expiration date. At first, it survives on imported capital equipment. Then that equipment ages. Then replacements must be made locally. If local industry cannot match the precision of the original, capability declines. Slowly, invisibly, civilization becomes less able to sustain the very systems that keep it alive. Human history offers a warning. Technologies can be lost, not because people become stupid, but because institutions, supply chains, specialists, incentives, and material flows disappear. Roman concrete, large-scale aqueduct maintenance, certain metallurgical techniques, long-distance administrative systems. Many capabilities have declined or vanished in regions where the supporting structure collapsed. Written knowledge alone is not enough. A technical civilization is not just information. It is practice embedded in a living economy. An isolated interstellar colony is therefore vulnerable to regression, even if it begins with extraordinary knowledge. If population falls below a threshold, specialization suffers. If a critical machine tool fails, entire branches of manufacturing may become impossible. If a rare catalyst is exhausted, chemical industries may simplify. If education narrows toward immediate survival, abstract science may become ceremonial rather than practical. None of these failures require catastrophe. They require time. This is one reason local environment matters so much. A star system rich in accessible metals, volatiles, stable orbits, and abundant energy may support a high-complexity civilization for millions of years. A poorer system may not. Expansion models that treat all stars as interchangeable dots miss this brutal detail. A star is not a colony site. It is a neighborhood that may or may not provide usable worlds, usable materials, tolerable radiation, stable orbital architecture, and enough accessible energy to resist entropy indefinitely. The stars themselves are temporary. Massive stars burn fast and die young. They offer energy, but not time. Sun-like stars offer billions of years, but not forever. Red dwarfs offer trillions of years, but often with flare activity, tidal locking challenges, and very different habitable conditions. White dwarfs cool. Stellar remnants persist, but are poor sources of convenient power unless technology becomes profoundly exotic. A civilization expanding through the galaxy does not build on permanent lamps. It builds on furnaces with different lifetimes, outputs, and hazards. Across millions of years, the galaxy also changes. Stars move. Spiral arms are not rigid objects. They are patterns through which stars and gas pass. Nearby stars drift into new neighborhoods. Molecular clouds form new stars. Supernovae inject radiation and heavy elements. Encounters disturb comet reservoirs. A route that once connected three useful systems may become less convenient as stellar motion alters the geometry. A map of the galaxy is not a permanent blueprint. It is a weather report written on a slow clock. This does not make local civilization futile. It makes galactic permanence suspect. The clearest way to state the limit is this. Any civilization has a coherence horizon. Inside that horizon, light speed delays are tolerable. Travel times are not absurd. Cultural drift can be managed, standards can be maintained, and mutual aid might arrive before it becomes meaningless. Outside that horizon, relationships become ancestral rather than functional. The horizon is not drawn by a border patrol. It is drawn by physics. Its size depends on the civilization. Its longevity, patience, energy, automation, biology, psychology, and tolerance for delay. A human-like civilization might have a coherence horizon of tens of light years. A very stable machine civilization might extend it to hundreds or perhaps thousands. But the Milky Way is so large that even thousands of light years represent only a small fraction of the whole. A galaxy-spanning empire would require a coherence horizon comparable to the galaxy itself. Known physics gives no reason to believe such a horizon is possible. Here is the central reversal. The problem with galactic empire is not that the galaxy is too hostile for intelligence. It is that the galaxy is too large for unity. Intelligence may arise, it may flourish, it may build habitats, artificial worlds, energy collectors, archives, telescopes, and local interstellar networks. It may travel farther than we can currently imagine. It may survive longer than species on planets usually do. But as it spreads, it becomes plural, it branches. It loses the singular identity that made the word empire meaningful. This conclusion is less dramatic than destruction, but more physically grounded. The Great Filter doesn't need to be a cosmic executioner. Civilizations do not all have to annihilate themselves. They do not all have to be rare. They do not all have to stay on their home planets. The galaxy could be inhabited by many local histories without ever producing one visible galactic authority. The strongest counter-argument remains. Perhaps our assumptions are too limited. Perhaps future physics will allow shortcuts. General relativity admits strange mathematical geometries, wormholes, warp metrics, exotic solutions where distances might be bent or effective travel times reduced. Quantum mechanics gives us entanglement, though not usable faster-than-light messaging. The history of science warns against declaring too confidently that the future will never surprise us. That caution is important. A science-safe argument must leave room for unknowns. We do not possess final physics. We do not know what a civilization 1,000,000 years older than ours could discover. It is possible that some part of nature still hidden from us changes the calculation, but possibility is not evidence. Under the physics that has survived experiment, faster-than-light information does not exist. Entanglement cannot transmit messages. Wormholes, if they exist in usable form at all, would require conditions we have never observed or engineered. Warp concepts require exotic energy arrangements and face severe theoretical problems. It is not honest to build a galactic empire on equations that are not known to correspond to buildable machines. So the stance is not never. It is sharper and more difficult. Without new physics that changes causality, the natural outcome of interstellar expansion is fragmentation, not empire. This has consequences for how we imagine our own future. If humanity ever reaches another star, the achievement will be almost beyond language. It will mean that biology born in one planetary ocean learned to survive the gulf between suns. But that success will also be a separation. The first true colony around another star will not be a remote province. It will be the beginning of another human-derived civilization. At 4 light-years, connection remains possible, but slow. At 40, it becomes generational. At 400, it becomes historical. At 4,000, it becomes mythological. The descendants may still remember Earth. They may honor it. They may preserve its archives. But memory is not governance. Reverence is not control. The farther they go, the more Earth becomes origin rather than capital. There is a sadness in that, if one expected conquest. There is also a strange beauty. A unified galactic empire would be a triumph of reach, but also a triumph of sameness. One command structure, one dominant value system, one civilization's logic extended across hundreds of billions of stars. Fragmentation would produce something less controllable and more diverse. Many islands of mind, each shaped by its star, its worlds, its accidents, its choices, its failures, its local physics. The galaxy would not become one city. It would become an archipelago. And perhaps that is the more plausible form of cosmic life. Look at Earth itself. Life did not remain one thing. It branched. Bacteria, archaea, eukaryotes, plants, fungi, animals, minds. Evolution creates diversity by separation, mutation, selection, and time. Interstellar expansion under light speed constraints would do something analogous to civilization. Distance would become the new ocean. Time delay would become the new mutation pressure. Local environments would become the new selection landscapes. What began as one culture would become many. The Milky Way may not be empty of ambition. It may simply be too large for ambition to remain singular. This view also changes how we interpret silence. If there are local clusters of intelligence scattered through the galaxy, most may never be visible to us. Their signals may not be aimed here. Their technologies may not leak detectable radiation. Their active phases may not overlap with our listening windows. Their languages may be incomprehensible. Their distances may be too great. Their artifacts may be local, not galactic. They may not build Dyson swarms around every star because they do not need every star. They may not announce themselves because broadcasting to the whole galaxy is expensive and mostly unrewarding. They may not even think in terms of being noticed by strangers tens of thousands of light years away. We look for empire because empire is visible. But nature may produce islands. The same reasoning applies to us. We have been a technological radio civilization for barely more than a century. That is nothing. A shell of our earliest broadcasts has traveled a little over 100 light years, reaching only a tiny bubble within the Milky Way. Most of the galaxy has no evidence that we exist. If someone 10,000 light years away is listening tonight, they are not hearing humanity. They are receiving whatever natural radio murmur Earth produced near the end of the last ice age. Our civilization has not yet reached them, even as information. We are not latecomers to a conversation. We may simply be inside a room whose walls are made of time. The practical future, if we are lucky and wise, may therefore be local. The solar system first. Moon, Mars, asteroids, orbital habitats, icy moons, deep space telescopes, perhaps industrial structures that use sunlight more fully. Then maybe probes to nearby stars. Then perhaps, far later, slow settlements in the closest systems if propulsion, biology, and ethics allow. A human sphere of influence, if it ever exists beyond the solar system, may be measured in tens of light years, not the whole galaxy. That would still be enormous. It would include many stars, many planets, many possibilities. It would be the greatest expansion in the history of life on Earth. It would not be the galactic empire. The gap between those two futures is the gap between exploration and dominion. One is hard. The other may be physically incoherent. This matters because our stories shape our expectations. If we imagine only empire, we may misunderstand both the limits and the opportunities. We may think the future is failure unless we rule the stars. But a civilization does not need to own a galaxy to become cosmic. It needs to endure, to learn, to expand responsibly where physics permits, and to accept that beyond some distance, descendants become neighbors rather than subjects. The universe may be telling us that control is the wrong dream. It is tempting to resist that lesson. Human history often celebrates expansion as power. Larger territory, larger networks, larger economies, larger states. But those patterns emerged on a small planet where communication time could shrink from months to seconds, and transport time could shrink from years to hours. Earth trained us to believe that distance is an engineering problem. The galaxy teaches a different lesson. Some distances are not problems to be solved. They are conditions under which identity changes. If a message takes 100,000 years to cross a domain, then that domain cannot behave like a single political body. If cargo takes centuries to arrive, then trade cannot function like an economy. If standards update slower than technology evolves, standards fragment. If colonies must be self-sufficient to survive, dependence disappears. If every local system fights entropy with local energy, then every civilization becomes rooted in its own star. The word empire belongs to worlds where centers can still reach edges. The Milky Way has no such center for us. There is another consequence, more philosophical but not less scientific. Intelligence may not be a force that overcomes the universe. It may be a pattern that the universe permits locally. A flame does not conquer thermodynamics by burning. It exists because thermodynamics allows energy to flow through it for a time. Life is similar. Civilization is similar. It is a temporary structure of order maintained by energy gradients. Stars provide gradients. Planets provide chemistry. Minds arise, act, build, and perhaps spread. But they do not step outside the laws that made them. The dream of galactic empire imagines intelligence as something that eventually dominates its environment. The physics of scale suggests intelligence remains embedded in its environment. It can rearrange local matter, it can harvest local energy, it can send messages and machines outward. But the larger the scale, the more the environment's deep structure reasserts itself. Light speed delay, energy cost, entropy, stellar motion, finite resources. The galaxy is not hostile, it is honest. It allows local miracles. It refuses total control. There is also a difference between visible presence and meaningful presence. And this distinction matters for almost every argument about the age of the galaxy. A civilization can leave evidence without leaving control. It can send probes into many systems without those probes being part of a living political body. It can build habitats around nearby stars without those habitats remaining aligned with the origin culture. It can even alter stars or asteroids locally without announcing itself across the whole disk. The absence of a visible empire is not the same as the absence of intelligence. It may simply be the absence of a structure that physics makes expensive to maintain. Consider what it would mean to occupy even a small sphere around the sun. A radius of 10 light-years sounds modest, and in galactic terms it is almost nothing. It is 1/10,000th of the diameter of the Milky Way. Yet even that small sphere includes multiple star systems, brown dwarfs, rogue bodies, comet reservoirs, and vast gaps where a ship in transit would be farther from help than any human mission has ever been. A civilization spread across that small neighborhood would already face multi-year communication delays and decades-long logistics for heavy cargo, unless it had propulsion far beyond ours. It would be an interstellar society, but a compact one. It would still be inside a local bubble. Expand that sphere to 100 light-years, and the number of potential destinations rises dramatically. The volume grows by a factor of 1,000. But the longest round-trip communication time becomes 200 years. A political decision made at the center would reach the edge after a century. The reply would return after another. In that time, local industries could change, local crises could end, local governments could be replaced, and entire generations could be born and die. A civilization that can remain coherent across such a sphere must be unlike any civilization we know. It must think in time blocks longer than human lives, preserve institutions with exceptional stability, and accept that most decisions at the frontier will be made without central approval. Expand to 1,000 light-years, and the word civilization becomes strained. The round trip from one side to the other is 2,000 years if the sphere is measured edge to edge, and longer for more distant pairings. The central archive might still receive reports. It might still transmit cultural material. It might still call the whole structure by one name. But functionally, the edge worlds are independent. They must be. No one can wait 2 millennia for instructions on matters that require action now. This is why the best version of a multi-star society is probably federal only in the loosest possible sense, more like a shared ancestry network than a state. It might preserve common myths, old scientific foundations, ceremonial calendars, foundational ethical principles, or agreed protocols for first contact between branches. But those are weak bonds compared to the practical forces of local survival. Local reality always wins eventually. The planet underfoot, the star overhead, the available elements, the radiation environment, the biology of the inhabitants, and the age of the colony will matter more than a message from a distant origin. There is a hidden assumption in many empire stories that technology makes distance disappear. On Earth, it often has. Telegraphs compressed continents, radio compressed oceans, aircraft compressed the globe. The internet compressed communication so dramatically that a person can speak across the planet in less than the time it takes to blink. This history trains the mind to expect every distance to be temporary. A far place becomes near when technology advances. But the history of Earth occurred inside a tiny arena where the speed of light delay is negligible. The entire planet is only about 40 milliseconds wide for light. A signal can cross Earth and return before the human nervous system fully registers a sound. The global internet works because, for human purposes, Earth is small. The Milky Way is not a larger Earth. It is a domain where light delay becomes the central feature of social reality. If you place 2 colonies 20 light-years apart, they can exchange knowledge, but not conversation. A message feels less like a phone call and more like a time capsule. A scientific paper sent from one to the other may still be valuable, but peer review across 40-year round trips becomes a different institution. A legal appeal is absurd. A trade negotiation becomes a multi-generational ritual. A personal letter becomes something a grandchild might answer. A war warning becomes a history lesson. A marriage proposal becomes a genealogical joke. Human emotion is not built for this. Perhaps machines are. But if machines are slow enough, stable enough, and patient enough to treat centuries as manageable, they also cease to resemble the social organisms that invented the idea of empire. They may become archive cultures, long-lived computational monasteries around stars, exchanging compressed histories rather than governing one another. That is a fascinating possibility. It is not the galactic senate of fiction. The nearest star problem also reveals the mismatch between public imagination and engineering reality. A mission to Alpha Centauri is often presented as the first step towards the stars, and it is. But Alpha Centauri is unusually favorable because it is the closest system, because its distance is known precisely, and because it contains multiple stars and at least one known planet around Proxima. The first interstellar probe will almost certainly target a nearby system because the energy and time costs are least cruel there. But a galaxy is not built out of nearest neighbor exceptions. Most destinations are not first targets. They are hundreds, thousands, or tens of thousands of light-years away. Even if the first probe succeeds, the temptation will be to misread it. A probe arriving after decades does not prove that settlement is easy. A flyby image of an exoplanet does not prove that a colony can survive. A laser sail reaching a star at 20% of light speed does not prove that a million-ton habitat can do the same. The first success will be real and magnificent, but it will belong to exploration. It will not abolish the hierarchy of difficulty. Settlement introduces another brutal filter: destination quality. Stars are not equal. A system may have no rocky planets. It may have planets but no accessible volatiles. It may have water locked deep inside icy bodies far from easy mining. It may have intense stellar flares, unstable orbits, giant planet migration scars, dense debris belts, high radiation, or no useful asteroid resources. A colonization wave cannot simply treat every star as fertile ground. It must survey, choose, and often skip. Skipping creates gaps. Gaps matter. If expansion relies on one colony seeding the next, and the next useful system lies far beyond the nearest star, the wave slows. If a region contains many poor systems, the wave may break into filaments, finding routes through favorable targets and leaving empty zones behind. If the favorable targets are separated by long voids, some routes may not be worth the cost. The galaxy's geography is not just distance, it is resource topology. A planet in the habitable zone is not automatically habitable either. It may lack a magnetic field. It may have a crushing atmosphere, no atmosphere, too much water, too little water, unstable climate, toxic chemistry, sterilizing flares, or incompatible geology. Even if it is habitable for microbes, it may not be usable for a technological colony without vast engineering. The most realistic interstellar settlements may not be on planets at all. They may be orbital habitats built from asteroids, powered by starlight or fusion, shielded by mass, and designed from the beginning as artificial environments. That option is more flexible, but it does not remove local resource dependence. A habitat civilization needs metals, volatiles, carbon, nitrogen, phosphorus, shielding mass, reactor materials, and replacement machinery. It needs not only a star, but a supply of small bodies that can be mined without excessive energy. Some systems will offer that, others will not. A wave of settlement will therefore be selective, uneven, and locally constrained, not smooth. The counter-argument of artificial intelligence changes the picture again. Machines may tolerate radiation better than humans, require no breathable air, reproduce from raw materials more easily, and operate at variable speeds. A machine civilization might send compact seed factories rather than cities. It might travel slowly and wake only on arrival. It might choose stars not for human comfort, but for energy and materials. It might build computational habitats around red dwarfs, white dwarfs, or even free-floating objects. This is the strongest form of the expansion argument because it removes many biological weaknesses, but it does not remove physics. A machine still needs energy. Its memories still need error correction. Its structures still erode. Its signals still move at light speed. Its copies still risk drift. If it becomes fully local and self-directing, it becomes another independent intelligence. If it remains centrally controlled, delay breaks control. If it is designed never to change, local environments punish inflexibility. If it is designed to adapt, adaptation produces divergence. The dilemma returns in machine form. One can imagine a civilization that embraces this. It sends out seeds not to rule the galaxy, but to multiply possibilities. Each seed carries a core ethic: preserve life, study, avoid harm, build only where sustainable, communicate when useful, and accept divergence. Such a civilization might not seek empire at all. It might become a cosmic ecology of related but independent branches. This future is far more plausible than a centralized galactic dominion, and also far more difficult to detect from afar. The energy accounting of such a seed strategy is better because the payloads can be smaller, but small payloads limit what can be carried. A self-replicating seed must build industry from whatever it finds. It must know how to mine, refine, manufacture, assemble, test, repair, and reproduce its own critical components. That requires either enormous onboard complexity or a very forgiving local environment. Real mining is dirty. Real materials contain impurities. Real manufacturing needs precision. The leap from copying information to copying a complete industrial base is often underestimated. Biology replicates because it is built from chemistry that its environment supplies, and because billions of years of evolution tuned it to local conditions. A self-replicating machine arriving in an arbitrary star system does not have that history. It must carry generalized competence. Generalized competence is heavy in design space. It may be possible, but it is not a magic word. There is also the ethical problem of unbounded replication. A probe that can copy itself across star systems is not merely a tool. It is a potential invasive species at galactic scale. A cautious civilization may deliberately avoid such systems because a small error in replication policy could spread irreversible damage. The very method that makes galaxy-wide diffusion easiest may be too dangerous for responsible intelligence to use freely. The absence of self-replicating machines in our solar system, if that absence holds, may tell us less about possibility than about restraint, failure modes, or the difficulty of designing replication that stays aligned over millions of years. Alignment across time is not simpler than alignment across space. A directive that seems safe in the first generation may become ambiguous in the 1000th. Local modifications made for survival may alter priorities. Copy errors may accumulate. Selection pressures may favor probes that replicate more aggressively, ignore costly safety constraints, or adapt in ways their makers never intended. If there is any competitive environment among machine lineages, evolutionary dynamics can enter. The result may again be ecology, not empire. Civilizations that survive long enough to think clearly about these risks may choose local depth over galactic breadth. They may build inward, richer habitats, better knowledge, longer-lived archives, more stable ecosystems, deeper art, closer relationships with nearby stars. Expansion may not remain the ultimate value once a civilization understands the cost. The human assumption that advanced life must colonize everything may be a projection of a young species still shaped by frontier myths and resource hunger. There is no law of nature requiring intelligence to maximize occupied volume. A mature civilization might conclude that sending out a few archives, probes, and seeds is enough. It might preserve the option of contact without trying to fill the disk. It might value stability over spread, diversity over uniformity, or minimal interference over cosmic engineering. Some civilizations may expand aggressively, others may not. The galaxy's silence, then, could be shaped not only by physics, but by choices made under physics. Still, even aggressive expanders meet the fragmentation horizon. Suppose one civilization launches daughter colonies every few centuries. Suppose those colonies are successful. Suppose each daughter eventually launches its own. After enough time, the family tree extends across a large region, but every branch evolves independently. The origin cannot revoke a daughter's decisions. The daughter cannot control its grandchildren at a distance. Far branches may not even know the origin still exists. At some point, the expansion wave becomes a genealogy so deep that the common ancestor no longer defines the living branches. This is familiar on Earth. A language family can share a root and still produce languages whose speakers cannot understand one another. A biological clade can share an ancestor and still produce forms as different as whales and bats. A religious or philosophical tradition can share a founding event and still branch into incompatible schools. Time plus separation creates difference. Interstellar distance gives separation a physical guarantee. The galaxy is therefore less like a territory and more like deep time made spatial. Every light year is also a year of delay. Every 1,000 light years is a millennium of separation. Distance is not merely where something is. It is when you can know it. This means that a galactic map is always a map of the past. When astronomers look toward the center of the Milky Way, they see it as it was tens of thousands of years ago. When a distant civilization looks at Earth from 10,000 light-years away, it does not see cities, aircraft, or radio telescopes. It sees a planet before agriculture. If it sends a message after noticing oxygen, oceans, or perhaps a faint biosphere signature, that message arrives in a future utterly disconnected from the observation that inspired it. This temporal layering makes first contact stranger than fiction usually admits. Two civilizations separated by 1,000 light-years cannot have a normal conversation. They can exchange monuments. One sends a statement of existence, the other replies to a past world. Each side learns about what the other used to be. Contact becomes paleontology with intelligence on both ends. Would that be meaningful? Absolutely. It could be one of the most profound events in any civilization's history. But it would not create alliance in the ordinary sense. It would create awareness across time. That may be the real form of galactic society if it exists. Not a government, not an economy, not a federation, but a slow exchange of deep-time artifacts. Civilizations broadcasting libraries to the dark, knowing that any reply will arrive long after the senders have changed. Archives designed not for conversation, but for inheritance by strangers. Messages written with the humility of ruins. In that version of the galaxy, patience replaces control. You do not ask for help. You send what you have learned. You do not negotiate. You testify. You do not command the far stars. You leave durable patterns of thought and hope that somewhere, somewhen, another island receives them. This is a very different emotional architecture from empire. It is less thrilling in the military sense, but far grander in the civilizational sense. It asks intelligence to accept that most of the universe cannot be made immediate. It asks us to become good ancestors rather than rulers. The physical reason is still the same: causality. In relativity, cause and effect have structure. Events separated by too much space and too little time cannot influence one another. The light cone is not merely a diagram in a textbook. It is the boundary of possible influence. A civilization is not just spread through space. It is spread through light cones. The farther a colony lies, the less it belongs to the present of the origin. Empire imagines one shared present. The galaxy denies it. Even the idea of a galactic capital becomes absurd. A capital works when news arrives fast enough and decisions return fast enough. On Earth, ancient empires strained even across months of travel. Provinces rebelled, governors improvised, borders shifted before commands arrived. Modern states work at large scale because communication and transport are fast enough relative to political change. A galactic capital would receive frontier news from thousands of years ago and send decisions into futures it cannot predict. The capital might still exist as symbol. Pilgrims might travel there over centuries. Archives might be stored there. An origin world might be revered. But it would not govern the galaxy. It would be a sacred ruin at the center of a family story. Military power fares no better. A fleet sent to enforce authority across 1,000 light-years arrives after a millennium or more, depending on speed. The rebellious system has had 1,000 years to prepare, change, collapse, move, or become something else. The fleet itself is a society in transit, subject to its own drift and politics. By arrival, it may not share the motives of those who launched it. Long-distance force becomes indistinguishable from migration with weapons. The same is true of rescue. If a colony suffers disaster 50 light-years away, a distress signal reaches help after 50 years. A rescue mission launched immediately may take decades or centuries to arrive. A colony that cannot survive that interval will not survive rescue. It must solve the crisis locally or die. Therefore, every viable colony must be designed as if it is alone. Once designed that way, it becomes politically and economically alone. This is perhaps the most devastating practical conclusion. Interstellar settlements cannot be fragile dependencies. They must be complete worlds. But complete worlds do not remain subordinate easily. If the origin tries to maintain dependence by withholding key technology, the colony may fail or rebel intellectually. If it gives the colony everything needed for survival, it gives it independence. There is no stable middle ground across light-year distances. The moral and practical choice converges. Any humane colonization must create autonomous daughter civilizations. The word daughter is more accurate than colony. A colony on Earth can remain tied to a mother country through ships, trade, military force, and shared administration. A daughter civilization around another star, if it survives, grows up. It cannot be kept young by distance. Distance makes it older in its own direction. Now return to the energy problem from another angle. Waste heat. Every computation, every engine, every factory, every habitat produces heat. A civilization cannot hide from thermodynamics. If it uses enormous energy, it must radiate waste heat somewhere. A galaxy-spanning empire harvesting many stars would, in principle, leave large-scale infrared signatures if it captured and re-radiated a significant fraction of stellar power. Astronomers have searched for some forms of such waste heat. The absence of obvious galaxy-scale signatures does not prove no advanced civilizations exist, but it does argue against common civilizations that convert entire galaxies into engineering projects. This supports the island model. Local civilizations may use substantial energy without transforming the appearance of the whole galaxy. A few systems heavily engineered, among hundreds of billions, might be difficult to detect from afar. A small cluster optimized for efficiency might not blaze as an obvious artificial anomaly. If advanced cultures choose local depth and modest external leakage, the Milky Way could host many without looking engineered. The absence of empire is therefore not only physically plausible, it is observationally compatible with what we see. The stars still look mostly natural. But natural does not mean empty. A forest seen from orbit may look like green texture. That does not mean no insects, birds, roots, fungi, or hidden lives exist beneath the canopy. Our instruments are powerful, but they are not omniscient. We are trying to infer cosmic civilization from faint light, limited time, and assumptions shaped by our own brief technological adolescence. A careful stance must hold both sides. It would be arrogant to declare that no one is there. It would also be naive to assume that because the galaxy is old, someone should have turned it into an empire by now. The physical constraints make that expectation too simple. The better question becomes, what size of civilization does known physics naturally permit? The answer may be neighborhoods, not planets alone and not galaxies, but stellar neighborhoods. Clusters of systems close enough for communication delay to be culturally survivable, close enough for occasional travel to matter, close enough for shared standards to persist, and small enough for energy and maintenance burdens to remain local. A neighborhood civilization might span 10, 20, perhaps hundreds of stars if its members are patient and stable. It might build wonders beyond our imagination. It might last longer than humanity has existed. To us, it would be enormous. To the Milky Way, it would be a spark. 1,000 light-year civilization would be vast beyond any human empire. It might contain millions of habitats, billions or trillions of beings, and technologies that appear miraculous to us. But in a galaxy more than 100,000 light-years across, it would still be local. This scale mismatch is the core of the matter. What is cosmic to a species may be provincial to a galaxy. There is humility in that, and perhaps survival. Civilizations that accept locality may endure better than civilizations obsessed with total expansion. Locality encourages redundancy, ecological fit, and patience. Empire encourages overstretch. The physics that prevents galactic unity may also protect diversity by making conquest impractical. A hostile civilization cannot easily dominate the whole disk if its fleets and commands are slowed by the same light speed limits. Tyranny, like cooperation, has a horizon. This is one of the more hopeful consequences of the argument. The galaxy's scale may make oppression local. A destructive intelligence could harm its neighborhood. It could consume or sterilize nearby systems if it became powerful and reckless. But conquering the whole Milky Way would be limited by the same barriers that limit benevolent empire. Distance protects. It also isolates. There is no purely comforting answer. The physics that saves distant civilizations from conquest also prevents them from easily helping one another. A galaxy of islands is rich, but lonely. Each island must solve its own existential risks. Each must survive its own technologies, stellar hazards, ecological mistakes, and philosophical failures. There may be wisdom elsewhere, but it cannot arrive quickly. There may be warnings, but they may come too late. There may be companionship, but mostly across archives and delay. This is the price of a large universe with finite causality. If humanity survives long enough to become interstellar, the first lesson may not be dominance. It may be stewardship of a small sphere. We may learn that the solar system itself is already enormous enough to occupy thousands of years of work. The asteroids contain materials. The outer moons contain oceans and chemistry. The Kuiper Belt contains icy bodies and deep cold. The Oort cloud may extend into the boundary between our sun's domain and interstellar space. Before another star becomes a home, our own system may become a civilization of worlds. Even that will test communication, economics, ethics, and ecology. The light delay from Earth to the outer solar system can be hours. A society spread across the solar system will already experience some fragmentation. Mars will not be Earth. Titan will not be Mars. Belt habitats will not think like planetary surfaces. The island pattern begins before interstellar space. The galaxy only magnifies it. This is why the dream of empire may be replaced not by pessimism, but by a more precise ambition. Resilience without control, connection without immediacy, expansion without sameness, memory without domination. A mature cosmic civilization might measure success not by the number of stars it commands, but by the number of independent futures it helps make possible. That idea changes the emotional tone of the whole subject. The old vision says, "One day we will own the stars." The physics says, "One day, if we are fortunate, we may join the stars as one more local phenomenon among many. We may become part of the galaxy's plurality rather than its ruler. The galaxy does not need to be conquered to matter. It needs to be understood. There is one more misconception worth separating from the rest. The galaxy does not need to be hostile to defeat empire. A hostile galaxy would be easy to imagine. Black holes, supernova, radiation storms, rogue planets, gravitational chaos. Those hazards exist, but they are not the core of the argument. The deepest barrier is not violence, it is indifference. Most of interstellar space will not attack a ship in any dramatic sense. It will simply demand payment in time, energy, and maintenance. It will let the ship proceed, and while it proceeds, centuries will pass, parts will age, cultures will drift, and the destination will become less connected to the departure point with every kilometer crossed. The slow nature of the barrier is what makes it so easy to ignore in stories. A wall makes good drama. A monster makes good drama. A delay does not. Entropy does not. A message arriving too late to matter is not a cinematic explosion. It is a quiet failure of relevance. Yet quiet failures are often the ones that shape history most deeply. States do not always collapse because an enemy burns the capital. Sometimes they become too large to administer, too slow to respond, too expensive to maintain, too internally diverse to govern by one set of rules. The galaxy turns that historical pattern into physics. A defender of galactic empire might say that sufficiently advanced artificial intelligence could model every colony so accurately that current information is unnecessary. If the central mind can predict the future of each node, then stale data may still be useful. This sounds powerful, but prediction across centuries of independent technological and social development is not merely a problem of computing power. Complex systems can be sensitive to small events that cannot be known from a distance. A local epidemic, a reactor accident, an unexpected mineral discovery, a philosophical movement, a charismatic founder, a rare collision in a debris belt, a mutation in a closed ecosystem, a new theorem, a failed harvest, a change in stellar activity. These events alter trajectories. Predicting them in detail requires information from the system, and that information arrives late. The central predictor can build probability distributions. It cannot know the present. It can estimate what a distant colony might be like. It cannot govern what it is like. There is a difference between forecasting a climate and commanding a storm. Another counter-argument says that civilizations could standardize themselves deliberately. They could freeze language, law, technology, and culture into durable forms. Every colony could be required to preserve the original protocol stack, the original units, the original educational canon, the original constitution. If drift is the problem, make drift illegal. But enforcement again requires communication and force. More importantly, stagnation is dangerous. A colony that refuses to adapt to local conditions because a distant origin wrote sacred standards may be less survivable. Local adaptation is not a failure mode. It is often the reason the colony lives. A rigid empire might preserve coherence by sacrificing resilience. A resilient network sacrifices coherence by adapting locally. The trade-off is not optional. It emerges from the fact that each star system is different. A third counter-argument invokes minds that are not bound to planets or biological cycles at all. Suppose consciousness becomes digital. Suppose entire civilizations run as software in computational substrates near stars, choosing subjective clock rates. They could slow themselves down to match light-speed communication. A message that takes 1,000 years externally might feel like a day if the society chooses to run slowly. In that case, perhaps the galaxy becomes socially smaller. This is one of the most interesting possibilities, and it deserves respect. Subjective time control could enlarge the coherence horizon. A slow-running machine civilization might treat century delays as bearable. It could reduce energy use, preserve continuity, and communicate with patience impossible for biological humans. But again, the gain is finite. Running slowly helps with waiting. It does not reduce the objective time required for repairs, stellar evolution, cosmic events, or physical travel. It does not allow a message to arrive before a supernova, a colony failure, or an unexpected local transformation. And if different nodes choose different clock rates based on local energy and strategy, synchronization becomes another problem rather than a solution. Slow minds may make interstellar neighborhoods more coherent. They still do not make 100,000 light-years immediate. There is also a thermodynamic price to computation itself. Information processing is physical. Memory must be maintained. Errors must be corrected. Heat must be removed. Substrates degrade. A digital civilization is not a ghost floating outside matter. It is a pattern in matter, dependent on energy flows and hardware reliability. It may be more durable than biology. It is not exempt from entropy. This point is crucial because many futuristic arguments smuggle in a hidden dualism. They imagine advanced intelligence as if it becomes pure mind, leaving mass, heat, and local resources behind. Physics does not support that escape. Every thought requires a physical state. Every archive requires a medium. Every simulation requires energy and error correction. A mind uploaded into a machine around another star is still a local structure fighting local decay with local power. The galaxy does not care whether the intelligence is carbon, silicon, plasma, or something stranger. If it has structure, it must be maintained. If it sends information, the information travels at light speed. If it uses energy, it produces waste heat. If it persists, it does so by consuming gradients that are finite in time. This is why the argument is not anti-technology. It is anti-magic. It does not say future civilizations will be weak. It says strength remains measured against the same equations. A civilization might move asteroids, build habitats the size of worlds, harvest starlight, engineer genomes, and create minds that run for millions of years. It might do all of that and still fail to be a galaxy-spanning empire, because the limiting factor is not only the size of its machines, it is the causal structure of the arena. A useful analogy is the ocean before radio. Islands could be settled, ships could cross, empires could exist, but only within limits defined by travel time, weather, supply, and communication. Distant colonies often drifted politically and culturally because the center could not respond quickly enough. Now enlarge the ocean until the fastest possible signal takes centuries to cross it, and the ships take even longer. At that scale, the island pattern is no longer a phase before empire. It is the stable state. The Milky Way is that ocean, except the water is vacuum and the waves are light cones. This changes the meaning of ambition. A civilization that reaches 20 stars has not failed because it did not reach 20 billion. It has achieved something enormous inside the physical size of its own coherence. A culture that lasts 10 million years around a cluster of nearby stars has not failed because it did not govern the galactic center. It has done what very few forms of ordered matter may ever do: persist, learn, and keep entropy at bay across cosmic time. The mistake is judging cosmic success by terrestrial imperial metaphors. Bigger is not always more advanced. More connected is not always more stable. Faster is not always wiser. The universe may reward depth, redundancy, and local adaptation more than it rewards endless outward speed. This has implications for the search for extraterrestrial intelligence. If we expect galaxy-spanning engineering, we look for enormous infrared signatures, altered stars, synchronized beacons, or artificial structures on scales visible across tens of thousands of light years. Those searches are valuable, and they should continue. But if the island model is closer to the truth, the signatures may be subtle, local, intermittent, and difficult to distinguish from natural astrophysics. The absence of obvious galaxy-scale artifacts would not be surprising. We would need to search for smaller footprints, unusual waste heat around individual stars, narrowband signals that are not meant for us, transient optical pulses, atmospheric technosignatures on exoplanets, or artifacts within our own solar system left by probes that passed through long ago. Even then, detection is not guaranteed. A civilization may choose low-leakage technologies. It may communicate by tight beams. It may place its habitats far from planets. It may use energy efficiently enough that waste heat resembles ordinary dust or planetary emission. It may be extinct by the time its light reaches us, or not yet born, in the light we see. The galaxy is not only spatially large, it is temporally scrambled. When we look at a star 1,000 light-years away, we see a millennium-old version of it. If a civilization there became technological 500 years ago, our telescopes cannot yet know. If it flourished 2,000 years ago and vanished 500 years ago, we may currently be seeing its active era while the civilization itself is gone. SETI is not only a search across distance, it is a search through mismatched slices of time. This temporal mismatch makes humility scientifically necessary. We should not rush from silence to emptiness, nor from possibility to certainty. The correct stance is patient tension. The universe is large enough to host many things, and large enough to hide them from one another. The original fantasy of galactic empire collapses under that tension, but a deeper possibility remains. The Milky Way may be a place where intelligence repeatedly discovers that it is local. Each civilization looks outward, calculates the costs, sends probes, perhaps settles neighbors, perhaps receives ancient messages, and eventually learns that the dream of total unity belongs to fiction. Then it builds where it can. It becomes rich in its own region. It listens. It sends archives. It protects its descendants from becoming conquerors or catastrophes. It accepts that the galaxy will never be one room. That acceptance may be a mark of maturity, so return to the message we imagined at the beginning. It leaves Earth tonight, perfect and patient, traveling at the speed of light. After 4 years, it reaches the nearest star. After a century, it has crossed only the smallest neighborhood. After 10,000 years, it has barely begun to matter on galactic scales. After 100,000 years, it reaches the far side of the disk, if it was aimed that way, and if it has not faded into the background. It carries news of us, but by then we are not the same. We may be gone. We may be transformed. We may have descendants under other suns who would not understand the language of the beam. The signal did everything physics allowed. It still arrived too late to make a galaxy one place. That is the quiet argument. Not that the stars are unreachable, not that civilizations are doomed, not that the Milky Way is empty. The stronger and more unsettling possibility is that the galaxy can be inhabited without becoming unified. It can contain intelligence without empire. It can hold countless histories that never merge into one history. Somewhere, if life is common, there may be civilizations looking up at their own skies and asking the same question we ask. Why is the galaxy silent? Perhaps their answer is the same one slowly forming here. The silence is not a wall. It is an ocean. Across it, islands may burn with light, each too far from the others for its fire to become a single flame. We are one island now, a young one, a fragile one, a brief arrangement of language, metal, water, memory, and sunlight on a small rocky world in the Orion Spur. We have just begun to notice the scale of the sea around us. We have sent a few machines beyond the planets. We have listened for signals. We have drawn spirals in textbooks and imagined fleets crossing them. The deeper we look, the more the galaxy answers with proportion. Yes, travel may be possible. Yes, settlement may be possible. Yes, diffusion may be possible. But empire, the coherent rule of a galaxy, asks for something more than courage and engines. It asks the universe to make light faster, energy cheaper, entropy kinder, and time more obedient. The universe does not appear inclined to do so, and maybe that is not a defeat. Maybe the future worth wanting is not a galaxy under one banner, but many civilizations becoming themselves in the long dark between stars. Not one voice shouting across the Milky Way, but many voices, each local, each shaped by its own sky, each discovering that the cosmos is too large to own and too rich to reduce to one story. The stars may never become an empire. They may become something stranger. A galaxy of islands, a silence full of distant fires, a universe where intelligence does not conquer the dark, but lights small regions of it, again and again, wherever physics gives it time.